Hello, everybody. Thank you for attending this session. This will be a joint presentation between myself, John Ferguson of Deepwave Digital, and also joining me will be Adam Thompson from the NVIDIA Corporation. So the majority of what we're going to be talking about in this presentation is how to leverage GPUs in modern software-defined radio. We will begin by talking about the current APIs and current ways that you can leverage GPUs for signal processing. And then we will move into some forward-looking things that Adam is working on at NVIDIA to help incorporate GPUs for signal processing applications into arbitrary APIs and how the GNU Radio community may be able to use that work in order to streamline some signal processing for the GNU Radio users. Then Adam will hand it back over to me, and I will discuss a particular machine learning application, and we will go over an end-to-end workflow that involves a hardware software-defined radio, CPU signal processing, and then using the GPU to do some automatic speech recognition using neural network computations. And so with that, I will jump right into it. So GPUs tend to be used for two key roles in terms of processors for software-defined radios. You can kind of lump them into two buckets. One is DSP and pre-processing, so we're kind of putting those two together, and then deep learning applications. So in terms of DSP and pre-processing, they're primarily used as accelerators to execute highly parallelizable DSP tasks. So things like FFTs, stuff like that. The reason why people really like using GPUs for this is because you're able to get speedups typically associated with hardware accelerators like FPGAs, but you are actually writing software. So it's easily adaptable, easily changeable, and much easier to program than something like an FPGA. But you're not having to deal with the lower throughputs that are typically associated with CPUs. In terms of deep learning, GPUs are known to be ubiquitous for neural network computation. They are also the best supported compute engine for all deep learning frameworks. And then based on what I just said a second ago about writing software, making it easily adaptable, that allows us to keep up with the ever-changing world of machine learning, or the rapidly changing world of machine learning. So what we're going to work up to today is to create this flow graph here. So what we ultimately want to do is have an end-to-end workflow that is interesting, that leverages hardware, CPU compute, GPU compute. We wanted to leverage signal processing, and we wanted to leverage machine learning. So the example that we're going to be showing here is receiving FM signals, demodulating them over using the CPU and GNU Radio, performing some automatic speech detection and automatic speech recognition using a combination of GPU, CPU compute, and then ultimately displaying that for the user. So think of this as kind of radio automatic speech detection. So if we look a little bit closer into what this flow graph would look like, and all of this is will be implemented in GNU Radio. So we start off with our sensor, the hardware aspect here. So we have an RF front end, and we have analog to digital converter. We then, because we're using GNU Radio, it'll initially go into the CPU memory. So we are going to have to do a data copy from the ADC to the CPU, which will do some filtering, some speech detection. So is there actually a signal there? Followed by a demodulation, and then we will need to get into the machine learning parts, which is the blue boxes here. So we'll do a MEL spectrogram, then have an acoustic model, and then look at various text candidates, and we'll rank and score those. Finally, follow that up with a language model to rescore them, and then display the most likely text output. So you can see that this is very much a heterogeneous compute problem. We're going in and out of CPU in GPU. We're doing machine learning, we're doing signal processing, we're displaying, we have hardware. We feel this is a great example problem. But when it comes to GNU Radio, one thing that you will realize is that when you start to do GPU processing, what ends up happening is the machine learning aspect of it, or the GPU processing aspect of it, tends to get lumped into one big group. So what we will end up having to do is taking all of these GPU processes, lumping them into one big Python block, and to be inserted into GNU Radio. And this is mostly due to making the memory management more efficient. Okay, so when considering doing signal processing with GPUs, there are a few things that we do care about. One is the ability to do high performance signal processing operations and an easy to use API. Okay, we care about throughput. We want to be able to do low latency, high bandwidth compute. And we want to, for this particular problem, we want to make sure that we're future-proofing this for various AI APIs. And then, of course, almost all compute for signal processing is complex valued. Okay, so what I'm going to do now is I'm going to toss it over to Adam, who is going to go through our outline, and then he is going to discuss the signal processing and pre-processing aspects of the presentation. Okay, Adam, to you.
So one of the themes of GRCon this year is about the integration of accelerators into the workflow. And as John mentioned in the introduction, one of the components and one of the accelerators that we find particularly important here are GPUs. And so GPUs are well positioned to do the fast signal processing that we care about in this community. But also on that same device, we can tie into deep learning and machine learning frameworks like NeMo for speech to text translation, so automatic speaker recognition tasks, or PyTorch and TensorFlow for things like modulation recognition and wireless fingerprinting and beyond. So we plan in this part of the talk to go over the current capabilities and limitations of the software products targeting signal processing and its connections to the GNU Radio community, and in addition, give some forward-leaning information about future APIs that NVIDIA are working on to push this community forward. So one of the libraries that you may be familiar with is CooSignal. So full disclosure, I am the creator of CooSignal. It is a pure Python interface to do GPU accelerated signal processing and borrows heavily from the open source SciPy Signal library. So CooSignal is all free and open source. Kind of the elevator pitch for CooSignal is if you are familiar with MATLAB's signal processing toolbox or with SciPy Signal, you can kind of get base GPU performance with minimal or trivial code change to your application. So we support probably 75 to 80% coverage of the API of SciPy Signal and have particularly expanded upon support for things like phased array applications. So we have an MVDR beamformer, for example, and some pulse Doppler processing. And we've also added support for things like a polyphase channelizer. So this is kind of like the classical polyphase channelizer with uniform channel sizes and all of that other stuff. So we have a full list of supported functions within the CooSignal documentation. And later in this presentation, there will be links of how do you download this and where do you see the code. CooSignal is all free and it's all open source. One of the things I want to hit on here, and this talk is not a CooSignal talk, so we'll go really quickly through the enabling technology stack. But fundamentally, the design philosophy of CooSignal was that if we're starting from scratch to build a library that's going to be widely used in the community and have a lot of interest and support, our goal was to get out features as quickly as possible. So feature first, performance second. And so the quickest way to kind of realize this was to focus and build our software totally in Python, okay? And so there are libraries that build on top of CUDA that expose Python bindings that we can leverage to kind of put everything together to create a signal processing software package, which is CooSignal. And so if you look at the SciPy Signal code, so looking just at CPU, you see a lot of NumPy, a lot of FFTs, a lot of matrix multiplications, as we are all kind of familiar with. And so we can say, let's leverage CooPy, which is a GPU accelerated version of NumPy, to do most of the work. And then we can fill in the gaps for performance. We can look for things like deep copies and try to minimize those. And then if there isn't support with a library like CooPy, we can create our own custom CUDA kernels via Numba. And so fundamentally, we have for free Python bindings down to custom GPU kernels, that we've built in this purely Pythonic environment. So this is what CooSignal is, right? It's all about quickly building signal processing code in Python. And so we have this recipe for crawl, walk, run, where first, if you're trying to build this new library like CooSignal, and the same kind of philosophy applies if you're not building something just for signal processing. But look for GPU library replacements. So if you see a lot of NumPy in your code, Control F and replace with CooPy. If you're a data analytics person and use a lot of pandas, Control F for pandas and replace with cuDF, etc. So these are kind of free, trivial code changes that automatically give you GPU support. And underneath the hood, all CooPy is doing is it's calling the CUDA math libraries. So you're not having this like massive Python overhead in your application. But not all things that we want to do. So the polyphase resampler is a good example of this. Not all of our applications exist in a drop-in library replacement. So we need to create CUDA kernels. And so we leverage Numba, which is a low-level virtual machine, to do this, and it really simplifies and gives boilerplate code to creating GPU-accelerated functionality within Python. And finally, if that kind of doesn't give you enough speed, or you want to go kind of as fast as possible, we can use these custom raw CUDA kernels. So essentially, this is C++ code that's wrapped into a string and put into a CooPy raw module. So this gives you native CUDA C++ speed, but it doesn't force this custom Python or PyBind software layer to do Python bindings. So let's take a look at the API. This is the CooSignal API. So here what we're showing is SciPy signal. So this is just CPU. We're going to do a quick polyphase resample, and we're just timing the compute here. So we're not timing the hosted device to the CPU to the GPU memory transfer here. And so if you time this, just the resample poly, this takes about 2.4-ish seconds on a Xeon E5. And as we move to CooSignal, everything you see in the code that's green is what's changed. So instead of instead of NumPy, we import CooPy. And instead of SciPy signal, we import CooSignal. So trivial code change here, right? And this is 285 times faster than the CPU on a V100. So CooSignal works on, it's not just these big data center GPUs, it also works on the Jetson Nanos. So any CUDA-enabled GPU, CooSignal fundamentally works. And one of the really cool key enabling technologies that CooSignal integrates is this support of what's called the CUDA array interface, which is a standardized mechanism for how we handle on GPU memory within Python. And so what you can do is you can do some fast pre-processing within CooSignal, and then you can move that data object to PyTorch with torch.asktensor. And if you display the pointers, you can see that the CooPy array that's denoted as SIG there and the torch array both have the same memory pointer. So there has been no additional memory copy as we have moved from CooSignal or CooPy or Numba to PyTorch. So you can join the CooSignal community. We have an active community, many of which are within GNU Radio. So I very, very much appreciate your support. And the conda install instructions are listed below, along with the GitHub repository. It's free and it's open source, and we highly encourage you to try it out. So if we look at CUDA acceleration into GNU Radio, there's been a couple of efforts to do this. We can provide generic CUDA interface for GNU Radio with GR CUDA. It has broad applicability, but is slightly difficult to use. And there's also been some efforts for, specific to some of the CUDA math libraries, so cuFFT interface to GNU Radio within GR Wave Learner. So again, this is kind of, it's easy to use or easier to use, but it's kind of limited in its operation. And so as we look to the future, the GNU Radio community, the ideal API kind of looks like a generic integration of a generic library that has been created that's optimized DSP kind of at the core level. So you let someone else do the math, the exposure of the CUDA managed memory, how do you handle streaming data, and then the GNU Radio community could take that library and wrap it into GR blocks, for example. So one of the libraries that we're working on specific to at NVIDIA is called MatX. And so what MatX is it's a C++ header-only library that's existing to unify the CUDA math libraries and place them behind an easier to use API. And so this is not public yet. We're working on getting approvals to open source this, which is going to be coming hopefully any day now. And so the way that someone like the GNU Radio community could use MatX is it's saying MatX is the engine from which you are integrating into GNU Radio. And so what the overall design goals and philosophies and API looks like is that, again, we're trying to get maximum performance by deallocating memory management from processing. So we introduce a concept of lightweight descriptors to our underlying data objects called views, and most of the compute that you do operates on these views. But when you do something like changing the representation of your data, so if you do a transpose, for example, you're just changing the view. You're not actually invoking any compute. And so again, the idea here is providing an easier to understand API within C++ that allows you kind of to get native GPU performance. And if you want to do FFTs and matrix inversions, you don't necessarily have to learn each of those libraries, right? You would learn MatX. And so what this library looks like is this is an example of just a very, very simple FFT-based resampler. On the left is what Python looks like, and on the right is MatX, right? So we have these tensor views, but then essentially we just call an FFT, we slice, and we do our IFFT. So one of the things that the GNU Radio community could do is to wrap a GNU Radio buffer into one of these views to execute a CUDA algorithm. So we have no additional data copy kind of once GNU Radio Scheduler supports these GPU buffers. So it's just kind of an idea of some of the fundamental DSP libraries that the GNU Radio community can build upon, particularly with the goal of making GPUs as an accelerator of choice to be more integrated into these workflows.
All right. Thank you, Adam. I am going to now jump right into the machine learning aspect of this presentation, and particularly I'll be talking about automatic speech detection, and we will be leveraging the NeMo toolbox to do this. And then we will jump into a demonstration of running this automatic speech detection stuff within GNU Radio on a software-defined radio, and then we'll provide a few kind of food for thought items, forward-looking implementations for GPU accelerators and other accelerators within GNU Radio. So if you're not familiar with automatic speech detection, it's basically the task of taking a raw audio signal and turning that into a text output. So you typically have a raw audio. In our case, we'll be doing 16K audio rate, so not super high audio rate. You then do some sort of processing or pre-processing to extract features. And then you run that through an acoustic model, then you run that through a language model, and finally you output the text file. And so that's kind of shown illustratively down here. So ASR, or automatic speech recognition, is a data processing pipeline just like GNU Radio. So, that would be beautiful if we could put various machine learning blocks in GNU Radio flow graphs, and we're hoping to be able to do that kind of in some future version of GNU Radio. These automatic speech recognition, or ASR algorithms, contain multiple DNNs, and they leverage CPU and GPU processing, making data movement and efficient data copies between accelerators very important. And of course, you can do the signal processing on the CPUs. You don't have, or the GPUs. You don't have to do that strictly on CPUs or FPGAs. So the implementation that we're going to be talking about is what we're calling Radio-ASR, or Radio Automatic Speech Recognition. And so we think you should care about this for a few reasons. You may look at it and say, well, demodulating a FM signal and doing speech to text, that doesn't sound like a difficult problem. Both halves of that problem are already solved. But we see it a little bit differently. The integration of these two disciplines, in particular for this problem, it is a great example of how to do that. So it really is a good example of integrating deep learning tools into radio flows. You should also care because we're only leveraging open source software stacks here. So we're looking at open source machine learning frameworks. We're leveraging GNU Radio, Python, all that stuff. And it's implemented in GNU Radio. So you'll be able to actually get this working in a GNU Radio flow graph. And also, it's an untethered implementation. So what we mean by that is you're not using an internet connection to send, your audio back to a data center or a large GPU in order to do the compute. Everything is happening within the radio. So there's a GPU on the radio, an embedded GPU on the radio that is doing the compute. And just generally, this is a great example of going from radio hardware to digital signal processing to machine learning for a real-world problem. So the real-world problem is we have a handheld radio that transmits over the air. The software-defined radio receives it, demodulates it, sends it to the ASR neural network that's doing the speech to text. So if you're not familiar, NVIDIA's NeMo toolbox is very, very useful. It's a toolkit to develop state-of-the-art conversational AI models, just like it says there. Essentially, it has a lot of tools that interact with different CUDA toolboxes. It leverages PyTorch or PyTorch Lightning. It contains libraries for ASR and LP, TTS, but very importantly, it has a lot of pre-trained models. So that means that you don't really have to train a whole bunch of models on your own. It works pretty well out of the box for voice recognition or natural language processing or speech synthesis. It supports English and Mandarin languages. And just has a lot of really useful, easy-to-use libraries. And this is what we have used for the Radio-ASR demo that we'll be showing here. We're putting the links down there at the bottom for NeMo, and all the links for all of the open source tools that we leveraged are at the end of the presentation. Okay, so now let's talk about the specific implementation that we have here for NeMo within GNU Radio. So here is our GNU Radio flow graph. You start off on the left-hand side. The squiggly lines there are the RF signal coming in. And then we get into GNU Radio where we have our SOAPy source block. So we are leveraging the Deepwave's ART radio here. And so we sample the RF data, and then we send that to a low-pass filter. We then run that through a power squelch. And if we break squelch, then that goes to a narrowband FM demodulation, and then we go to GNU Radio's Python block, where we have created an embedded ASR code in there. So you will see, if you look at this embedded Python block, and we have the code down here below, what we are doing is just leveraging the built-in Python block. And you'll notice a couple of things. One, on line 3, we're importing from our Radio-ASR, we're importing a speech inference tool. And that is the main function of the work of the work function here in the Python block. The reason why that is, basically everything is contained in a separate function is because we have to leverage GPU compute in order to do this. And as of right now, GNU Radio does not handle GPU buffers, so that we kind of have to put it all into one big blob of Python code, so to speak. But let's look at what that big blob of Python code looks like. So here I'm showing kind of the overview of what the Radio-ASR algorithm does. So we have a 16 kilohertz audio rate coming in from our demodulator. And then we do our pre-processing. So that would be a MEL spectrogram. If you're not familiar, a MEL spectrogram, basically instead of having evenly spaced frequency bins, it divides it up into frequency bins where each bin is about what the human ear can detect. So it's based more on the human ear resolution. And so it ends up being kind of like a log scale. So we go through the MEL spectrogram where we have frequency versus time. Each time bin is 20 milliseconds for this algorithm, and then the z-axis is power. Once we have our MEL spectrogram, we then go through QuartzNet. So QuartzNet is a pre-trained model available with NeMo, and it turns each of these 20 millisecond columns into a probability distribution of which letter of the alphabet it is. And you'll see that we have 27 characters because we're including a space. So the 26 letters of the English language plus a spacebar. Plus a space character. So, if it's the highest probability is B will be, like 80% probability. So you end up with that distribution for each column, and each column then gets converted to the most probable letter. We then run that through a text candidate algorithm. This basically runs through a dictionary and says, what is the most likely case of what these words are. So this is actually a CPU process. Currently, there's no reason why it couldn't be on a GPU, or many algorithms will combine it with the acoustic model. But at the end, what you end up with is a beam of, we call a beam of text. So each row represents a specific sequence of characters that are words that are to be looked at and fed into the language model. So you define how many beams you want to find. And we chose 24. And then finally, you send that to a language model. This is a neural network that is executed on the GPU. And so you take those 24 beams and you rescore them. So from the text candidate section, each beam had a probability with how accurate we think it is. You rescore those now with the language model, and that's what you end up outputting is the most probable beam there. So a few things to note here. This is a heterogeneous compute problem. So we are going CPU and GPU, transferring memory between. The entire flow ends up being a single Python block, as I mentioned before in GNU Radio. And so we end up having to build that as standalone Python code and then implement that in GNU Radio. Call that from GNU Radio. But if you look at it, it really looks a lot like a GNU Radio flow graph. So in an ideal world, we could make each of these independent GNU Radio blocks and be able to move memory between them, which is hopefully something that we should be able to do in a future version of GNU Radio. Fingers crossed. So the platform that we chose to implement this on is Deepwave's Air-T. This makes it, this platform makes it super easy to do this because it's got the built-in NVIDIA Jetson GPU. Block diagram is shown there on the right-hand side. So it's got the analog devices 9371 chip. Data goes to a Xilinx FPGA. That FPGA does decimation of the data down to the rate you want. RDMAs it over to the NVIDIA Jetson. The NVIDIA Jetson is really nice because it has shared memory between the CPU and GPU, so we don't have to have extra memory copies once we're in that world. It runs, Ubuntu 18.04, makes it very easy to program on, and ideal for this type of problem because of this memory management that is taken care of for you. So what we have done, we've implemented all of that GNU Radio flow graph, so we're operating in GNU Radio here. This is untethered speech to text. We have demonstrated that this has the ability to work with broadcast FM. So we, demodulate NPR and stream that to a text file. GMRS is the one I'll show you in a second. So that's demodulating narrowband FM. That's handheld radio that like you see there. And then we use Nemo for all of this. So Nemo-ASR running natively on the RT using the GPU. And you'll see the GPU only leverages about 7% of the GPU cores for this processing. So what I'll show you now is, if you do want to see this actually function in the real world, the Deepwave people over at our booth at the GNU Radio Conference will be running this live, and you'll be able to talk into a two-way radio and see the speech to text. So all of this is from pre-trained models using Nemo. And what I'll show you here is Jeff Zarita, who is going to be at the booth, spoke the Gettysburg Address into a two-way radio. And we received that with the ART and ran the Radio-ASR algorithm over it. Yeah, so you see it's not perfect. It used the word fourth as in the number as opposed to fourth as in brought forth. So it's not perfect, but it is a great demonstration of how to do this and an excellent place to start to build, any machine learning algorithm with that includes signal processing. Okay, so looking forward, all this was great. We had to jump through some hoops, though. So what is it that we would really want? And this isn't meant to be dictating what the GNU Radio community should be doing. It's more meant to just kind of be food for thought. But ultimately, wrapping machine learning and GPU processing into a single block is kind of cumbersome. It's definitely not very modular, and modularity is one of the key aspects that makes software-defined radios appealing. So in an ideal world, we would want independent GPU blocks or independent machine learning blocks that can process each one of these steps. And it looks like that might actually be possible in future versions of GNU Radio where they're going to handle GPU buffers. So future architectures, we believe, are going to contain heterogeneous compute. So we need to be able to move data easily between FPGAs, CPUs, GPUs, and maybe even neural processors when they become mainstream. And then Adam spoke to MatX. We think that its ability to leverage views and that API's ability to interact with commercial APIs such as GNU Radio is going to be very, very useful going forward. Especially as soon as GNU Radio is able to handle GPU memory. So with that, I will speak for myself and Adam and say thank you very much for your time, and I hope you enjoyed this talk, and we will stick around for any questions that you may have. Last but not least, references. So here is all of the open source libraries that we leveraged for this work.